All right. Hi, my name is Clarissa Carretta. I'm a geology major. My faculty mentor is Dr. Daniel Irmas, and my project is a rapid method for estimating soil chemical information using soil color. Just some background to start off with. So soil color is related to soil composition, and soil composition is affected by pedogenic processes. Pedogenesis refers to the processes that form soils, and pedogenic processes are the processes that further contribute to the evolution and development of soils over time. Three coloring agents that are known in soils are soil organic carbon, iron, and manganese. Soil organic carbon and manganese are both known to have a darkening effect on soils over time and with increasing concentration, and iron is known to have a reddening effect in the same conditions. But there is a big difference between the two properties of soil color and soil chemical composition. One is a qualitative property, and one is a quantitative property. So soil color is a qualitative property. It's something that can be assessed in the field just by observation. As you see in this photo, the assessor is taking a piece of the soil and putting it up to this Munsell color chart, which I will discuss later, and is able to make a field-based determination of what the color of the soil is. But the chemical concentrations of constituents in the soil, that is a quantitative relationship. It requires sampling in the field, and it requires for that sample to be taken back to the lab for further analysis. So the big idea and question we had going into this was if we could draw a quantitative relationship between the soil color and the concentration of these constituents in the soil that are known to color the soil, could we perhaps make a field-based estimation of these concentrations just based on the observation of the color in the field? So why is this important? Well, it's important for many reasons, but three specific ones are land use, soil mapping, and soil taxonomy. I'll just give one example of why it's important in soil mapping. So many times surveyors are sent out into the field to do wetland delineations, which is determining where a wetland begins and ends. And to determine where the wetland is, it often requires to know the concentration of constituents like iron, manganese, and soil organic carbon, determine if the concentrations are high enough for it to be considered a wetland. So if we were able to just look at the color of the soil in the field and say, oh, if there's a correlation between it, we could say, oh, because it's of this color, perhaps we can estimate this amount of content of said chemical constituent. And this could really help out people who are in the field making these decisions, because lab analysis takes time to sample the soil and take it back into the lab. So these rough estimates in the field could help with decision making and mapping and things like that. So soil color is measured using the Munsell color system, which is pictured here on the right. It works on these three axes. So I'll just go through an example to explain how it works. So in this example, the color is 5YR51. First, you would identify the hue, which is just the overall color of the soil, and that is the main color of the soil. There may be other pockets of color in the soil, but we just want the main matrix color of the soil. In this case, it would be a YR, which is a yellow-red, as you see on this axis. The next you would do is the chroma, which is on this protruding axis right here. In this case, it's a 5 on the color intensity scale, so the yellow color intensity scale. So the yellow-red color would be a 5, which is about in the middle of the scale. And then the value comes last, which is the lightness or darkness of the color on this center axis right here. In this case, it's a 1, which is pretty low, so it would be a pretty dark soil. The overall purpose of this study was to analyze the relationship between soil color and the concentration of soil organic carbon, manganese, and iron. And we also wanted to see if we could build a predictive model to predict the concentrations of these chemical constituents just based on soil color and a couple other properties that I will share in the next few slides. So for the data collection for this study, we did not do the actual in-field sampling. That was done by NEON. So the soil was sampled at NEON megapit sites nationwide. I'm just going to go to the next slide for a second to show you where these sites are. They're the green circles. As you can see, they're spread all across the country in many different environments. And it's a very widespread range of sites. So the soil was sampled at these sites. It was described in the field by the technicians and then sampled and taken into the laboratory where it underwent the standard soil, physical, chemical, and mineralogical analysis. So through that analysis, we were able to get the actual concentrations of these constituents in the soil. Step 3 is where I came in. So these reports, which are available on the NCSS soil characterization database, I was able to go download those. And then I had to go through a months-long process of turning those descriptions, which were written in basically paragraphs of soil descriptions. I had to turn those into usable data that could be used for analysis in R, which that means it needs to be numerical data. So I had to change those descriptions into numerical data and put it into a spreadsheet. This was a pretty long process, but I was able to make the data set this way. And also I was able to merge the lab data with the soil descriptions, which came from 2 different places. These were the 3 lab analysis methods used to determine the concentrations of the constituents that I used in this study. So first is the major element analysis, which was used for iron and manganese. Just determines the amount of the element in the soil, and it's done by acid digestion by nitric acid and hydrochloric acid and measured in milligrams per kilograms. And a big component of this is they wanted to maximize the amount of concentration measured while minimizing the interaction with the matrix of the soil. So that means all the other components of the soil that were not relevant to this major element measurement, they wanted to minimize that. The next measurement that we used was the total carbon measurement. This is the sum of organic and inorganic carbon in the soil, which should be noted because we were unable to find the concentration of just the organic carbon. So in this study, it's both the organic and inorganic carbon. It's measured by dry combustion and measured in percentage in the soil. And lastly, the citrate dithione extraction for iron as well, which is just a measure of the free iron in the soil. This should be noted because there is known to be an increase of free iron with increased weathering, and this is known specifically to affect soil color and is also measured in percentage. So in order to determine if there is a correlation between the concentration of these chemicals in the soil with the color, we need to develop a pedotransfer function, or a PTF. What a PTF does is take known soil properties that are commonly measured and use numerical modeling and regression to turn it into properties that are much more difficult to measure. And so just to give an example, which the example is what I did in the study. The known soil property in this case was the soil matrix color, depth and texture. Depth and texture were included because those are also known to have a big effect on the soil color. The PTF was the stepwise model, which I will explain in the next slide. And the target soil parameter we wanted was a prediction of the chemical concentrations of the 3 chemicals. So this is just going to go through what we did in R to analyze the data and determine if there was a relationship. So first step was to convert those Munsell color data into RGB values. As you saw before, the Munsell color, it includes a letter in the color notation, and in R you cannot use notation like that. So we needed to convert those that color data into numerical values. So it was converted into RGB values, which are just 3 numerical values for redness, greeness, and blueness in the color. We also averaged those soils that had multiple colors reported and different percentages of those colors reported. So after those were converted to numerical values, we were able to run the full model with all interaction terms. So the full model included as the independent variables, the soil color, the texture in the form of sand and clay content, and the depth of the horizon. And the dependent variable was each chemical constituent. After running the full model with all interaction terms, we did a stepwise regression in both directions. So in this process, the stepwise regression will add and delete the independent variables in order to find the model that best predicts our target prediction. So in the forward direction, it will start with 1 independent variable, for example, color, and it will add each variable on until it gets to all 6. And then in the reverse direction, it will start with all 6 variables, take them all off until it gets back to 1 variable, and it will see which of these interactions between the variables are the most impactful and most important for predicting the chemical constituents. Next was a regression of the measured versus predicted values. The predicted values are from the stepwise regression, and I will have graphs showing this to better explain it. And next was a validation of the model through multiple jackknifing. In this process, the data set is split into 70-30, and 30% of the data is run through the stepwise model to validate it and to see what R-squared values comes out of that. It went through 2,000 rounds of multiple jackknifing with a random data set of 30% of the data set selected every single time. And from the multiple jackknifing, we were able to determine some R-squareds that I will show in the next few slides. So this is the first one I will show. This is the iron major element analysis. So on this chart, by the way, the next few slides will have both these charts. I'll just explain what they are now. So on the y-axis, we have the measured iron, which is the reported values from the lab analysis. So we know what the values are measured to be. And on the x-axis is the predicted iron. And this is predicted from the model that included, from the stepwise model, which could include the RGB values, the texture, and the depth. So in this case, you can see that the predictions based on the model they do pretty well on the lower concentrations of iron, but on higher concentrations of iron in the soil, they do not predict as well. And the R-squared value of 0.3985, it means that 39.85% of the variation in the predicted iron is explained by variation in the soil color and those other independent variables I shared. And this one on the right is the distribution of R-squareds that came from the multiple jackknifing, so 1 through 2,000 iterations of the model, and it came up with all these different R-squared values and put them on this histogram to show the distribution. And the mean R-squared that came out of this histogram is 0.2464. So as you can see, it does drop down because it selects random sets of data, which can include any of these points, including the outliers, and bring down the R-squared value. Next was the citrate dithionite, which was noted to have an effect on color specifically, and it did have a higher R-squared value of 0.4556. As you can see, again, it predicts iron pretty decently in lower concentrations, but struggles to predict it accurately at higher concentrations. And here's the distribution of R-squareds again. And as you can see, it did not drop as much as that first one did, meaning that this model is better at predicting iron. Next was manganese. This model did not do as well. As you can see, it had a lower R-squared value, so only 33.51% of the variation in manganese concentration is explained by variation in color, as can be seen by this graph and the distribution of R-squared values here from the multiple jackknifing. And finally, the soil organic carbon had the highest R-squared of 65.09% variation in the soil organic carbon concentration explained by the color. And you can see the distribution here of those R-squared values again with the mean R-squared. So some conclusions from this preliminary study. Some variation in chemical concentration can be explained by variation in soil color, which was shown by the R-squared values in those graphs. And soil organic carbon is best predicted by the model as seen by the highest R-squared value, and manganese was the most poorly predicted by the model. And iron extracted by citrate dithionite showed a better prediction than the iron extracted by acid digestion in the major element measurement. I apologize, I think this got messed up a little bit, but all of the models predicted lower concentrations more accurately than the higher concentrations. And for future work, I hope to continue building up my data set that I've been working on for close to a year now and continue doing analysis on that data. I'd also like to focus analysis on more specific categories like specific types of soils, or specific regions, or specific particle sizes in order to see more correlation between soil color and chemical concentration in those types of soils. And also I'd like to find the inorganic carbon data from the data I already extracted to be able to subtract it from the total carbon and redo the model with only the organic carbon data. Finally, I'd like to say thank you to my faculty mentor, Dr. Daniel Ermas, for all his help on this project, and here's my references. And thank you, that is all.
Thank you very much, Clarissa. Wonderful. So again, we have